morning, everyone. Thank you for coming to this RAS discussion meeting on quenching galaxies at low and high redshifts. I'm Chris Sintor. I'm one of the large SOC that put this together. We hope you enjoy it. I do need to tell you that there are fire exits. You have presumably read the slides which explain where they are, but there's an exit there and any of the doors at the back will work. If you want, of equal importance, if you want to tweet about the meeting, then the hashtag is RAS quenching, and we are being live streamed. So when we get to questions, we will have people bringing mics to you. So please wait for the microphone to reach you before you say anything. If you don't want to, if you're in the audience and you don't want to appear on the live stream, then save your questions for the coffee break or talking to the speakers afterwards. With that, we can get started. Our first speaker and invited talk is the wonderful Katey Alatalo from Space Telescope, who's going to tell us about the life cycle of gas in quenching galaxies. Katey, over to you.
Thank you, Chris, and thank you for coming and for inviting me. Apologies that I was slightly late. Public transportation is not something that Baltimore, Maryland, or America knows a lot about, so I'm a little new to the whole process of being able to go places without cars. So the first thing we always like to do is we like to thank our collaborators. I have an enormous list, and in fact, I even have to put a catch-all list, given how many wonderful people I work with a note that I am highlighting students that I work with specifically on many of these things, because I also know some of the students and collaborators I work with are in this room. So I was tasked to give, an overarching review of quenching galaxies, but in particular trying to bring you up to speed on some of the new things that we've learned. I don't make assumptions about our audience. For many of you, this is probably going to be review, but for some of you, I hope this is sort of new. So since about, let's say, 1936, we've known that galaxies come in specific flavors. The chaos that we see in the sky when we look up and we try to look at every single galaxy and figure out what it is breaks down actually fairly simply. What I'm showing here, I will say, number one, I need to thank Galaxies Zoo, the Zooniverse, and Karen Masters for these diagrams, but they break up in a nice sequence. We can actually even reduce them slightly further by thinking about this morphology sequence as bimodalities. So on one side of the bimodality, you have late-type galaxies. On the other side, you have early-type galaxies. Now, we also can actually blame Edwin Hubble for this particular nomenclature, because unfortunately for us, astronomers do not change easily. Ask yourselves about the magnitude system for a second and think about the Greeks. But late-type galaxies, it was actually because Edwin Hubble thought that the sequence went, the sequence went from here, from this side to that side.
You do it with a laser pointer.
It's fine. We're going to see if I can do it without. So late-type galaxies tend to be blue star-forming. They tend to have spiral structure. And early-type galaxies actually are evidence of something that is lacking, which is they lack spiral structure. They come in sort of two different forms. They come in the elliptical form right here, and they come in the lenticular form. So there's another bimodality that, again, started to be noticed very early on, was advanced quite greatly by an amazing astronomer lost far before her time, Beatrice Tinsley. But Sloan really revolutionized this, which is that the bimodality in morphology also has a paired bimodality in color. So when you actually try to show what the morphological bimodality looks like on this plot, where again you can see two peaks and a dearth in the center, wow, you find late-type galaxies lie sort of in the distribution. They tend to actually fit in the bottom where they're bluer, but there's a nice big wing that goes into the upper parts. And early-type galaxies sort of fit up at the top in something we call the red sequence. But something else you should notice is that though we do see this bimodality, we do see that blue like late-type galaxies, that is spiral galaxies, cluster down towards the bottom, and early-type galaxies are sort of clustered up at the top, there's a significant overlap. So, for instance, you would not be able to take the color of a galaxy and automatically know its morphology. So we ended up pushing this just a little bit further, and we looked at infrared data, which, again, was another thing that we could do that was revolutionary, because we went from having the Sloan Digital Sky Survey, which covered this enormous portion of the sky. It gave us millions of spectra and millions of data on galaxies. The WISE spacecraft was able to do something very similar in the infrared sky. And so we did a very similar thing. We took the galaxies that were nearby and we classified them and we put them in infrared color space. And what we saw is that there was actually an even more distinct breakdown between early type galaxies, that is, red, spiralless, dead, elliptical lenticulars, and late type galaxies, which were these blue star-forming spirals. So the great news was when you actually put them together and looked at them as a sequence, that sequence became even tighter, so that you could potentially use the combination of optical colors and infrared colors to tell you a bit about the morphology of the galaxy. So, at least for me, and maybe for you, the thing you should actually be asking is, this is great. We're seeing these emergent bimodalities in our galaxy distribution. Edwin Hubble published a book in 1936 where he mentioned these things. That's wonderful. But is this bird collecting, or is there some underlying physics to that? Now, obviously, if I ask the question, I'm probably doing so rhetorically. It's true. So the answer is yes. So if you look at simulations of merging galaxies between, say, two late-type gas-rich star-forming galaxies, if you smash them together in simulations, this actually goes all the way back to 1945 when Holmberg did the first study of this using light bulbs for his mechanical computer. You find that because of the way that the angular momentum breaks down, you can create a nice elliptical galaxy. You can create an early type from the merger of two late types. Great. The other bimodality also has a physics that you can understand about it, which is if you look at colors and you say, for instance, put a model. No, I can't do it. If you take a model of galaxies, maybe I do want the laser pointer, Chris.
Yeah, you can still use the mic as well, Katey.
Yes, so I will. There we go. Oh my goodness, it is very bright. If you put a model. Oh, don't worry about that. If you take a model of a single galaxy and you just let it basically form stars, and then you decide to turn off star formation, very rapidly that galaxy's colors change. That is, when you no longer have, say, your bright blue O and B stars forming, a galaxy fades very, very quickly. So again, these things are great. I've told you a little bit about how mergers can cause morphological change. As you can see, the mergers also were able to cause color change. And I told you that star formation being turned off can create this change. Now the problem is you should be asking the question, well, what turns off star formation? Mergers do, but maybe other things do. Well, if we want to understand what turns off star formation, we need to be able to find these objects. Looking at a Milky Way does actually teach us a lot because the Milky Way is a very complex system, but it doesn't teach us everything. So let's say I wanted to understand every single way I could quench star formation that existed. Well, that means that I want to find every single galaxy that is undergoing this transition. So we start here. This is the amount of time I have where these galaxies are not sitting unambiguously in one sequence or the other. Caveat being, obviously, things are fading slowly. Oftentimes, we actually call this the post-starburst phase. So in this phase, you search for galaxies that have rapidly quenched their star formation. You look for a couple of things. In the past, sort of the traditional way to do so, was what is called the E plus A or the K plus A selection. And those two selections look for a dearth of star formation that is happening right now, and they look for evidence of intermediate aged but not infant stars. This phase is about 100 meg-years in duration. Again, signs of young stars, no star formation. The galaxies that we find spectrally and are able to classify as this are found in the Green Valley, that is in that gap between the two modes. And these things can be found both in merger remnants and in non-interacting galaxies. But there's a problem. So the problem is this: not all quenching galaxies go through this phase. It could be because the geometry of the merger is such that when we point our telescope from Earth on the line of sight from Earth, just the galaxy has too much dust obscuring this particular sign from us. But more importantly, because again, one of the ways that you find a lack of infant stars is you find a lack of H2 regions, because young stars, 10 meg-a-year or younger, create a lot of H-alpha emission. You miss other things that create H-alpha emission. For instance, you miss things that have active galactic nuclei, and you miss things that have shocks. So basically, I looked at this prescription and I said, well, what can we do to expand this a bit? Well, I care about finding intermediate age stars, and I care about finding a lack of star formation. And again, the traditional way we did this is we looked for signs of A star, Balmer absorption, and a lack of H-alpha emission. But there's another way to do it. Perhaps, instead of focusing on the lack of ionized gas, you can use the ionized gas itself as a diagnostic. So what we did is instead, we looked for ionized gas ratios that were inconsistent with star formation. So what you're seeing here is the ionized gas line ratio plots with models based on some extraordinary work Lisa Keeley did that showed basically where you could find these line ratios, where star formation could create these line ratios. And we basically took everything and we looked at things that could be inside of this boundary, which is actually the boundary available and permissible from shocks. And we cut out anything that was sort of below this line, because that was a lot of star formation. Being the good astronomers that we are, we also created an acronym. So Balmer absorption, again, is a very, very good way to find intermediate age stars. A stars are very good at creating very deep Balmer absorption lines. But we looked for shocked ionized gas ratios instead of looking for the lack of H-alpha emission. And then we started to call these galaxies shocked post-starburst galaxies, or SPOGs. I will warn you now, SPOGs will possibly be the only thing you take away from my talk that actually defines an effective acronym. It's an acronym that even if you don't like, you remember. So forewarning. So we plugged this criterion into the Sloan Digital Sky Survey, and we looked for the galaxies that, again, fit this stellar absorption suggesting intermediate age stars, and the ionized gas ratios being inconsistent with pure star formation. And when we did that, we had a parent sample of about 160,000 galaxies we could look at, because we required that they be observed and detected in all of the ionized gas lines in those 3 diagrams. And we found 1,067 of them fit the criterion we put in. They exhibited intermediate optical colors. That's great. Again, green colors don't mean that you're quenching, but it is sure nice to say, I think this galaxy is quenching, and find that it's green. They have a lot of neutral gas absorption, which unfortunately this talk is short enough I can't get into, but you can talk to me. They have a high incidence of radio emission, and a large proportion of them were detected in molecular gas. We have put this sample online, so if any inquiring minds want to actually go and look at these galaxies and do, extraordinary things we haven't thought of yet, that sounds great, please do so. So, I'm going to back up a little bit again. I've now told you about why these galaxies are interesting, about the fact that physics is underlying these bimodalities, about some of the ways that we can expand how we find them. But let's go back and think about actually what we are looking at physically. So when we're taking a galaxy from blue to red, we look for about 3 things. The first that happens is some transition trigger occurs. The event ignites the galaxy's transformation from blue to red. It's often external in origin, but not always. The second thing that occurs is the star-forming fuel must be removed. Again, you have to quench star formation, which means that the fuel for star formation can't be forming stars. So the gas must be forming stars, again, must be rendered incapable. and star-forming fuel is removed is kind of an interesting thing. And finally, so the easiest manifestation, the thing that is easiest for us to find as observers, is that the stellar population fades. But again, that's sort of the very last step, when the young blue stars are no longer forming and the A stars are starting to slowly fade and your galaxy is going from blue to red. But the thing that's important here is that this transition, this road from blue to red, is paved with gas. A galaxy's gas is the linchpin to understanding its evolution. We need to understand what its gas is doing. So, I'm going to posit something to you. I'm going to posit it confidently, though, because I think I'm going to be able to back up two statements that challenge the conventional knowledge, but I don't think necessarily completely break it, which is cold gas does not get completely expelled before a galaxy quenches its star formation, and cold gas in transitioning galaxies exhibits inefficient star formation. So the standard framework for galaxy quenching looks something like this. You have two galaxies, they merge. Again, in this case, that is the quenching trigger. Some point the AGN is active. This is Markarian 231 for a few megayears. And at that phase, we actually made the assumption that gas was being blown out of the galaxy. So if you thought about it and you looked at where gas was and then where gas was no longer, molecular gas is here. At the AGN phase, boom, the gas is completely gone. At that point, the galaxy goes through its post-starburst phase, that is its quenched star formation phase. And then it fades into sort of quiescence. Great picture, made a lot of sense. It's one of the reasons why explosive AGN feedback was important, because you needed a step in a galaxy's transformation where the gas was violently and rapidly removed from the system, which is actually what we assumed this step to be, and why, when we predicted where the molecular gas was no longer going to be present in the galaxy, we put it right here. But, and again, I will back this up, it turns out when we actually observed these types of galaxies, that was not true. It actually appeared that molecular gas sort of disappeared into being non-important to the galaxy beyond and sort of into the post-starburst phase. So the gas was there when the star formation quenched. And we sort of think that this timescale is about a gigayear, but again, we're working on it because this is actually fairly new. Now, when I say this, I'm just positing this. This is coming from these points that I'm making. I need to back it up. So I will. Work in about 2015, done by Decker French and Kate Rowlands, a little bit by myself, but mostly by Decker and Kate, started to show that post-starburst galaxies, that is not the way that I selected them, which was to predetermine that they probably had gas, but the ones that lacked H-alpha emission still had significant reservoirs of molecular gas. And by significant, I mean that there were cases where they had, molecular gas fractions of 10%. That's pretty large. Decker's study in particular showed, again, she was looking at these classical E+A selected galaxies, found that 50% of them had significant reservoirs of molecular gas. And again, there's their molecular gas fraction compared to, in this case, Amélie Saint-Onge's cold gas. Kate Rowlands, doing a completely independent selection of post-starburst galaxies, also was finding significant reservoirs of molecular gas. And then, when we started pointing either the ERM 30 meter or Karma, may it rest in peace, at SPOGs we started to find significant reservoirs of molecular gas. So despite the fact that these galaxies no longer had existent star formation, they had reservoirs of gas that was completely capable of forming stars. So what does that mean? How do you actually do that? So how do you kill star formation inside of the gas? Well, let me introduce you to the molecular gas blob and the turmeric Q parameter. So Q is a way that we basically parameterized gravitational energy balance in star formation. So up here, we have the kinetic energy terms, we have the gas dispersion, we have the rotation of the gas, which will drive Q up. On the other side of the equation, in the denominator, we have the gas surface density, which drives Q down. When Q is greater than 1, gas is stable against gravitational collapse. when Q is less than or equal to 1, gas is gravitationally unstable, and it will form stars. So that has a manifestation in the observations. So this is the fairly famous Kennicutt-Schmidt relation. Now again, I don't want to assume everyone in this room is a galaxy evolution specialist, and I certainly don't want to assume everyone in this room is a star formation parametrization specialist. So I will tell you about what each of these things means. So on this axis, we have the star formation surface density. That is the amount of star formation that is happening per unit area in the galaxy. And on the bottom, we have the molecular gas surface density, which is the amount of molecular gas per unit surface area. And again, there is scatter, but this line right here sort of represents where about 1% of molecular gas is being turned into a star per a characteristic time of the galaxy. Dynamical time, also free fall time, depending on what theory you work with and believe, or how advanced your theory becomes. So that's great. For the most part, given that the Kennicutt-Schmidt relation primarily was studying for a very long time star-forming galaxies and merging galaxies, so galaxies that have not yet quenched their star formation. This is great, and this works. 1% turbulence inside the system is probably what regulates it. Wonderful. Well, let me introduce you to some of the outliers. So here we are again. So let's start by putting, I don't want to say the least exciting because Tim is in the audience. But yeah, you'll see. Gas-rich early-type galaxies fall about 2 to 5 times off of the Kennicutt-Schmidt relation. This means in every individual galaxy, if you just put it on the Kennicutt-Schmidt, it's within the scatter, you don't really care. When it's a population that are all showing that trend, it gets interesting. So we actually started studying some compact group galaxies. They fall on average about 10 times below the relation, with some that are up to 50 times suppressed. That means that they have molecular gas that should be forming stars and is 50 times more inefficient than 1%. And then finally, there are sort of the most extraordinary things on this, if we judge extraordinary based on distance from average, which we can all argue about, because maybe that's not a good definition of extraordinary. And NGC 1266, which is an AGN outflow, molecular gas outflow host, falls 70 times off of this relation. And post-starbursts, again, these are these E plus A characterized things, can fall between 10 and 70 times off of this relation. So that means that we're starting to see that there's a diversion from this thing that we had always assumed was normal, or we always assumed was sort of standard. But again, we didn't know early-type galaxies had molecular gas for a really long time, and we certainly didn't know post-starburst galaxies had reservoirs of molecular gas still capable of forming stars. So let's go back to our picture of a molecular gas blob. So if you inject turbulence, that is, you drive up CS, into the gas, you rebalance the energy equation, and you compact gravitational collapse. Q increases, and forming stars becomes more difficult. You've done it. Star formation is now suppressed. That's great, but there's a problem. Fine structure lines also turn on when you're driving turbulence into something, and they start cooling that turbulence out. That means that in these systems, while the turbulence does an excellent job, again, rebalancing the energy equations, giving you less efficient star formation, you actually have to find a way to drive that into the system fairly continuously. So what does that mean also for our old picture of the quenching sequence? It means that rendering cold gas infertile by suppressing star formation will actually allow it to survive a galaxy's quenching. So the gas can remain in the galaxy, not forming stars. And a galaxy does not need to expel its cold gas because it can transform if you just inject turbulence into the gas and keep it from forming stars. So to me, that sort of leaves a couple of outstanding questions. Now that, again, we've kind of come to the idea that we need a completely new paradigm for how we quench galaxies after the triggering mechanism. How common is star formation suppression in galaxy transition? I didn't talk about the multitudinous ways in which galaxies transform. I talked about mergers mostly, but if a galaxy falls into a cluster and is being REM pressure stripped, are you going to see this? Again, does the interstellar medium feed back and all those things? And what is the redshift evolution of quenching? So, in summary, the emergent bimodalities in galaxies underlies physics of how galaxies transition from blue star-forming spirals to red ellipticals and early types. SPOGs opened a new phase space for us to identify quenching galaxies, which is good because that's fairly necessary, because we're only now starting to understand that galaxies that are undergoing quenching are maintaining molecular gas that should be forming stars, that is now again defying the convention not only of how galaxies transition, but how molecular gas in galaxies is supposed to form stars. And the future is bright. Again, we found some of these things with single-dish millimeter interferometers. And now we have ALMA, so we not only can study this thing in great detail, i.e. actually being able to parameterize the turbulence itself in these galaxies, we're going to be able to study galaxies to high redshift, for instance, to see if high redshift quenching galaxies show these same things. So I thank you, and we'll take your questions.
Thank you very much. What a great overview and some excellent questions for us to ponder. Questions from the audience? Brooke.
So if the gas is still there, what causes the turbulence, and could it shut off and then it reforms star formation instead of this being a unitary sequence that goes to red all the time?
So the gas is still there, yes. The galaxies we've studied in enough detail to know what does this. For the best case study out there, which is my favorite galaxy, NGC 1266, it seems to be that the AGN goes through a duty cycle where gas collapses in, turns on the outflow sort of stirs up the gas, most of the gas falls back in, injects turbulence, keeps star formation from happening. In the compact group galaxies that I had that one little thing, that little slide on, it's actually just the group environment. You know, when you're in a chaotic group environment, you're interacting very, very frequently. But because it's chaotic, the interactions and the gravitational torques are able to be maintained for much longer than, say, merger and coalescence. So in that case, we can point to where we think the injected energy is. In the case of the post-starburst, though, we're kind of puzzled because in many of those cases, post-starburst galaxies, especially from the E plus A characterization, are selected against having AGNs because AGNs are very happy to give you H-alpha emission, for instance. So right now what we're trying to do is find out if a sort of dinky duty cycle of injecting turbulence via an AGN is energetically capable of basically maintaining these gas reservoirs for a gigayear, which is kind of the of order we think that this is happening on. And the answer was, even in NGC 1266, we broke physics. Yeah.
More questions? Tim.
Very nice, thank you. As you know well, there's two terms at the top of that queue. You've also got your kappa term, and that can be very important too. Obviously, it's probably a cycle where your velocity dispersion increases first. You end up forming a bulge through your quenching mechanism. Is there a way we can work out what's important at which phase? How do we push forward and work out which of these terms is the most important and when?
Well, obviously we need a very large sample of these to study. So basically, like, we have to go for more and we have to go for higher resolution are kind of the two things that we really, really need. We need to have stellar population analysis that is accurate enough to tell you how far after the quenching event you are, because you want to see the difference between something that quenched 100 megayears ago and something that's right on the edge of sort of becoming completely quiescent. And you need to have resolution that is capable, again, to determine the difference between intrinsic gas velocity dispersion and beam smearing due to rotation. So you basically need to have scale height level measurements of your gas combined with, an accurate picture of star formation in a set of galaxies that like to contaminate every star formation tracer to try to understand this better. So on top of it, I will say that tumor Q is probably not the correct way we should parameterize this. I did mostly because I had these slides beautifully constructed and I wasn't going to go to the virial parameter yet, but really what we want to be doing is actually looking at the virial parameter in this. And the great news is I have an extraordinary undergraduate student named Diane Salim who's going to be putting a paper out fairly soon that actually is able to show how changing the virial parameter is directly able to change the star formation efficiency. So all of those things are good. It's hard. We need high resolution. We are going to be chatting, I'm sure, today about ALMA proposals that we are both working on.
Good. Probably got time for one more quick one if there is one in the audience. Otherwise, Tim, let's take a question here. But Tim, do you want to come and set up while we're doing that?
So you mentioned for the quenching there needs to be a trigger. So the example you gave was that of a merger. But if you have, say, a galaxy in isolation that's not entering a cluster and not merging with another galaxy, how would you expect it to stop or to start the path of quenching?
That's a really good question, Quaranta. I think it seems like minor mergers actually can be really important. So as long as the galaxy has a lot of companions that are constantly sort of bombarding it, that can also sort of set up your critical bulge to be large enough to do this. And it's very possible that, again, the quenching mechanisms we're looking at are in violently quenching galaxies at this point. We're going to want to do a better job studying other things. And again, this is the kind of case where I can turn you to Tim's paper on the Atlas 3D sample to look at sort of how some of that suppression is even maintained by things like, big bulges and galactic shear.
Good. Thank you. Well, let's thank Katey again for an excellent start to the meeting. Thank you.